a center tap that is buried in the ground. That is ground. So from ground to this line, you've got 120 volts AC. From this ground to this end of the line, you got 120 volts AC. If you want to run something that takes a lot of current, the rules for electrical distribution inside your house say you can't really go higher than 20 amps without using a special kind of outlet, special kind of wiring. So bigger appliances like an electric range, air conditioning, that uses, heavy current for the compressors outside, you need 240 volts. So line to line, you're going to have a 240 volt circuit available in the house. The white wire that's buried in the ground, the neutral wire, is the center tap for that. So here's what you got going here. The voltage you see in your house is actually that neutral wire. It's usually white. That's the convention. And you got the high side, high potential, and that one is black. Yeah, you're used to things being red and black with a battery. That's true. For low voltage DC, it's usually red and black. That's the convention. For house wiring, it's white and black, and the black one is the dangerous one. It's the one that's actually higher in potential than ground. So you touch a kitchen sink or something that's grounded, that's you, and you get a hold of this guy, and you get a hold of the kitchen sink, and the current flows through you at those lethal rates, and you're in trouble. So what they've done for safety is they've taken this neutral wire and they buried it in the ground, as I said. And the idea is that the newer plugs, ever since the 50s, have a third prong. And that one's called earth ground. And it too is buried in the ground, and it's usually colored green. And here's what we're going to do. We're going to build ourselves a toaster. Two slice. Cute little lever in here to make everything pop up. And this box is made of metal. So we're going to take our three prongs, and two of them are going to go to the coil in there. And the third one, the long one, the neutral one, is going to go to the box itself. Now, what should happen, and by the way, the wider one is neutral, the narrower one, that's the hot side, this is the neutral side. The white prong is neutral, and if it happens with your misfortune that this guy breaks or this guy touches the metal box, all of a sudden this metal box is hot. And if you touch it, and you touch this kitchen sink, which is connected to a cold water pipe, which is going to the ground, you've got a complete circuit through you that looks just like that. And it's going to hurt. And it could be fatal. So now what they do is they take the earth ground and connect it to this. And what do you really have? This hot side touches earth ground. You got a short circuit. It takes out the breaker, but it doesn't go through you. It goes through an alternate path. That's the reason why I got three prongs. Two of them are carrying power. The third one's purely for safety. To make it work, they took one of the two wires, the neutral one, and they buried it in the ground outside your house. If you actually look at, if you have overhead wires, you'll probably see two black wires, and you'll probably see a steel cable, and the steel cable somewhere gets buried in the ground. Or when it gets to your house, it gets clamped to a cold water pipe. That's the neutral wire. When you look in your breaker box, there's a thing called a bus bar, and all the white wires for your breakers are connected to it. It's the return path for all your 120 volt circuits. In the case that you need 240 volts, the convention is you are going to switch both sides for safety. And if you look in your breaker box, some breakers have a single toggle, some have two toggles. If they have two toggles, they're switching this stuff.
Draw a picture and show the two buses in the circuit breaker box to show your 220 and your
Yeah,
10
okay.
and your white wire.
So you got a circuit breaker
Not
box.
everybody's ever looked inside of one.
You're going to see a metal bar here with a bunch of drill holes in it. This guy is connected to earth ground. That's your neutral return. Then you're going to have your two 240 volt lines coming in, here. It's not two 240s, between them is 240 volts AC. It's called line to line, that's the two black wires. Your circuit breakers are going to, which are just nothing but switches that operate with a trip device when the current is exceeded, are going to be connected to this 240 volt line. The return path for all these guys is going to be connected to the bus. So you're going to go 240 volts in through a breaker to your load. It's all your outlets in the house. Where the high side is going to go to the short one, the neutral side is going to go to the long one, and the earth ground is going to be connected to earth ground. And what's going to happen is 240 through the breaker to the outlets. The return path goes to the neutral, which is this guy, which happens to be the center tap of the feed that goes into your house. Let me know if I lost anybody here.
So if you take your meter, you should go across the two hots, that's how you get your 220.
You measure from here to here, you're going to see nothing.
110.
You measure from here to here, you're going to see 120 volts.
Yeah.
Because it's half of the stuff coming in the house. It's the center tap of this. It's neutral to line. It could go either way. It could go neutral to this end, neutral to that, and they try to, that's why there's two feeders. They try to balance it. Half your circuits
But
go to
your
one
electric dryer,
line.
your high
Your high current
appliances
devices that require the higher voltage
use both lines,
are going to be connected like this. You're going to have a breaker here
a double breaker.
and a double breaker. That's right. And they're getting together. And they're going to connect to this line and to this line. And I put the thing there just to show they're coupled together. I use a dotted line. And then out they go, and there's 240 volts here. And that'll kill you faster. So that's another reason why they still have the neutral. Because if either of those two lines breaks and touches the metal container, they want an immediate short circuit to bring out take one of these breakers down. And as long as we're on the subject, let me throw out one more device. Ever hear of a GCFI?
Ground fault.
Or GFCI, ground fault circuit interrupter? How does that work? Well, beautifully, of course. What makes it work? It's an incredibly simple device if you take one apart and look inside. I'm going to kind of use a.
We'll create a hot tub.
Yeah, here's what you got. You got
Nowadays.
normally it's a rod of a single rod like this, but I'm going to kind of for illustration purposes, I'm going to use a circle of iron. And what you got is here's your AC circuit. You know, it doesn't matter which is which. One is hot and one is neutral. And one of these guys is wrapped around this core and goes off its merry way to the load. And this guy goes around this core and goes off its merry way, except this guy is going one direction, the other guy is going the opposite direction. Each one will produce an opposite magnetic flux, and they'll balance each other, so there'll be a net flux of 0. What they do is they take a third little piece of wire here, and that's connected to a switch. And when you energize it enough, there's a coil. And when it gets energized, it'll make the switch open up. So guess what's going to happen? You're touching your toaster, and one of these wires at the same time, and the current flowing in this path is not going to equal the current flowing in this path, because instead of going back through here, it's going to go through you into the ground, right? Because your body is touching, your body is actually touching something at ground potential. When you get this imbalance, if the current here does not equal the current here, you have a net flux that does not equal an opposite, which means this thing gets energized and it opens the switch. It's that simple. Two runs of wire, each half of the circuit wraps around the coil, but in the opposite directions. They produce counterbalancing fluxes. And if they ever get out of balance, they energize a third coil, which pulls the switch to save your life.
Since it's
Every
ground-
bathroom, every place you have water, every place you have a sink, every place that has anything where you can touch a ground circuit should have one of those. Because if you find yourself in between the hot side and earth ground, you're going to be the conducting path. What makes it fatal? Well, you stuck your fingers on the prongs of a socket and pretty much lived to tell about it because the current was flowing through this short path where your fingers are. When it goes across the heart, it can cause arrhythmia or cardiac arrest. If it goes through your brain, it can cause stoppage of your respiration. That's when it becomes dangerous. They put the guy in the electric chair, they usually put a current path through his head and through his arms, make sure the job is really complete. They don't just want to smoke him, they want him to be fast and painless. That was, by the way, what Edison was trying to do to prove that AC was dangerous. He was killing livestock with alternating current. Well, he could have killed it with direct current too. There was absolutely nothing proven by that experiment, but he scared a lot of people. Didn't scare Westinghouse. Westinghouse won the contract. Niagara Falls used alternating current. Edison had to go back and kind of be pro.
There was a show I saw on PBS talking about inventors like Rockefeller and all those.
They're called, Men Who Built America.
Yeah, and they were talking.
And they were all Robert parents, except maybe Ford was a
They
nicer
said
guy.
Tesla invented AC while he was working for Edison.
Yeah, Edison promised to pay him
Edison didn't
$50,000
want
for one of
anything to
his
do with it.
inventions. So I don't remember promising that. And, okay, schmuck, I'm out of here. Basically, Mr. Tesla said, okay, I guess I can't work for you because you're dishonest SOB, and he went off on his own. But he didn't get enough money out of what followed because even though he came up with absolutely fabulous inventions, the people he was working for, like Westinghouse, didn't have enough money to pay him either. But he didn't care. He just wanted to see this stuff brought to the world. He had great ideas for how to, make current flow through the earth. He had these great demonstrations where he would touch a Tesla coil, which had very high voltages, but it wouldn't kill him because it had very low currents.
And they said Edison said DC is safer because it would be a lower voltage.
And he proved this
That
by
was his
saying,
thing.
okay, here's some alternating current. It was almost the radio frequencies.
Yeah.
And it went right through him, and it didn't do any harm at all because the current was very, very low. He had a Tesla coil, which had a primary like this and a secondary like this. But, while the voltage was stepped up by that ratio, this thing had so much impedance because he used very thin wire that the amount of current was like, microamperes. And that, just going through the skin, which has about 200 ohms of impedance, wasn't really that dangerous. You might feel tangled, but,
But it looks scary with all the lightning bolts.
oh, because you got a spark. Guess what this was? By the way, this thing exemplifies another one of his inventions that is in your car. The ignition coil. What's that all about? In your car, you got a 12-volt battery. Usually each one of these is a cell. There's 6 cells typically. Let's just draw a few of them. So this thing's 12 volts DC. And there's a breaker circuit here. It used to be something under the distributor cap. There was a cam
Points.
that would open a set of points that would, if you have, let's say, a V8 engine, it had 4 lobes on it because every rotation of it takes 2 rotations of the crankshaft before you need to detonate the fuel. There's an intake, compression, power, and exhaust stroke. So the piston's going up and down twice. The crankshaft is turning twice for every time you need a spark. You draw air and fuel in, valves close, you compress it. Now you detonate the fuel air mixture. That's the only time you do. And you have a power stroke and you have an exhaust stroke. So, yeah, there's a 4-lobed cam there on a V8 engine that would open the points. And what you got is current flowing. And when you get current flowing, you got a magnetic field. And when you open the points, guess what happens? The magnetic field collapses. What happens when it collapses? You've got a dV/dt, you've got a changing magnetic flux, which will produce a huge spike of voltage, typically about 30,000 volts worth. And that's what makes the spark plug. Have a spark bridging the gap. It takes about, what do they tell us, for every millimeter, it takes about a kilovolt to bridge that gap in open, in here. And you'll say, but lightning has to go miles to get from the clouds down to the ground. How does it do that? When, obviously the voltage isn't that high. The answer is, you got a cloud up here, and you got all these charges up here, and the charges get there because when the air moves, the friction, it's just like shoving your feet on a carpet, separates the charges. And, you get the opposite charges on the ground. And this potential, remember what an electric field is? Wherever you have different charges, you have a field in between them. And that field takes all the atoms in between and starts stripping electrons off and produces air molecules that have missing electrons, which means they are now ionized, which means they now conduct electricity. So what you're doing is you're building a field. You're actually creating a conduction path. And when it gets conductive enough, you get the lightning, which is nothing more than a big electric spark. If you are ever out in an open field and you feel your hair tingle, run like hell. In any direction you can. Just get away from wherever you are because you are about to be struck. That's a conductive path being built by those charges, and that's where the lightning's going to go. There's a very sad picture of three boys in Northbrook who were kind of posing for a picture and their hair was standing up on end. And after the picture was taken, they were dead because the lightning killed them. They were exactly in the wrong place. And the person taking their picture and these three kids did not know that. It's happened about 40 years